And good afternoon, everyone. My name is Perry, and I'm a master's student from Southern University of Science and Technology. I'm going to present our work to you, which is about realizing efficient motion planning method for continuous robot in dynamic environments. Continuous robots have the characteristic of high flexibility, adaptability, lightweight, and safety. And these robots are widely used in industry from manufacturing to healthcare. Currently, many applications related to continuous robots rely on precise and safe navigation. However, the complex redundancy characteristic of continuous robots pose challenges to their computational modeling and solution development. And especially when facing the dynamic environment, achieving efficient and safe motion planning will be crucial for this robot. So our motivation is to address the complexity of planning this robot in dynamic environments. Past research have achieved important milestones in past planning for continuous robot in static scenarios, and most of them utilize optimized methods for smooth and safe navigation. However, this method often struggles to meet two major challenges. The first challenge is that the most existing research focuses on static scenarios and overlooking the challenge posed by moving objects. And this may cause accidental collision during the actual planning process. And the other one is the complex kinematic of continuous robot, which exacerbates the difficulty of planning, and which may lead to inefficient paths and increased computation times. So our work aims to bridge this gap and propose an efficient planning method for continuous robot navigation in dynamic environments. So our proposed method can be expressed in a framework. So we first use piecewise constant culture method to construct a model representation of the robot, and then we substitute the model into the planning framework. The planning framework consists of three components. Firstly, we use optical sensing module to track the robot and optical through motion capture system and mark place in the environment. And by combining the PCC method with sensor data, we can obtain the robot configurations and optical information. The second module is the global planning part, which uses an algorithm based on the safety constraint RT-star-based method to quickly generate the initial paths. And this path takes into account the unique kinematics of continuous robots and dynamic optical information. The planning process can ensure that the robot's body complete the obstacle avoidance during the planning process from a geometric perspective and safely enter the motion phase. Finally, the local planning part, it refines the path generated by the previous module and use a visual feedback controller to complete the planning process and analyze the path point and environmental information to generate the actuation for the robot execution in the real world. And this can make precise and practical adjustment to the robot motions, achieving local planning and control of the robot. And this trio of methods work in harmony, enabling the continuous robot to perform its planning tasks effectively, ultimately transmitting the precise driving command to the controller for planning movement. The safety constraint RT-star-based method mentioned in the global planning part is shown like this. And this method uses these two equations as the core mechanisms, and which respectively implement the control that conform to the local kinematics and the optical avoidance at the geometry level. When we integrate them into the framework based on RT-star to achieve efficient motion planning. By setting planning key points and search space, we can generate the motion planning trees and paths. And this combination allows for efficient and collision-free planning in three-dimensional space, and providing a robust solution for the navigation challenge of continuous robots. So to weigh the effectiveness of our method, we utilize single and dual dynamic opticals seldom in the simulation environment. The result is that our method can ensure the collision-free planning paths and avoid collisions during the locomotion, maintain the optimal robot posture during the planning process. And this emphasizes applicability under different optical conditions. Building on our previous simulation, we explore the performance of RT-based and RT-star-based algorithms in scenarios with multiple obstacles. And our simulation results indicate that although the success rate of both algorithms decreases as the number of obstacles increases, the RT star consistently outperforms than RT in path efficiency with trajectory averaging 70% to 25% shorter than those generated by RT. And this efficiency is crucial in the dynamic environment and highlighting the potential of RT star for applications requiring rapid and precise navigation. In our real-world experiment, we explore the capability of our method by setting up two inflatable balloons as the dynamic obstacles. And we use orange cross point as the initial position and green cross point as the target position. And we introduce a motion capture system to check the markers attached to the robot's joint. And this allows us to obtain the robot's configurations and use a visual feedback controller to complete the planning and control process. So in conclusion, our work developed an efficient RT star-based planner for continuous robot and achieve high-quality passes with less computation time. Our simulation and experiments have shown its effectiveness in managing the complex dynamic environment. And in our future work, we will concentrate on refining the avoidance strategies and enhancing the roboticness to effectively manage an obstacle of unpredictable shapes. And additionally, we plan to expand our experimental scenario to include more complex environment, particularly in some narrow search spaces. And for more detailed information, you can scan the QR code above to access our paper. Thank you for your attention.
I have a question. Thank you for the talk. I know the goal is to avoid obstacles, but if it does actually touch an obstacle, can the path planner handle those cases, or would you need some sort of external sensor in order to do so?
Okay, thanks for the question. Our research only focuses on the obstacle avoidance and the feasibility of the 3D space. It's not for the practical application. So when facing the collisions between the robot and the obstacles, we will make some trade-off of this one. We have a cost function and we will focus on the value of the cost function. We may collide with the obstacles. We will let the robot's configuration to get away from the obstacle, but the end effector will get as close as possible to the target points.
Thank you.
Thank you. So, any other questions? If there's no any other questions, so thank you very much. And